A star dies, and for a few milliseconds, the universe squeezes a solar mass into something no wider than a city. What remains is not quite a star, not yet a black hole, but a neutron star, a place where gravity flattens mountains to millimeters, matter forgets the shape of atoms, and magnetic fields can twist space into bursts seen from across the galaxy. Welcome to Boring Science Stories. In this slow journey, we'll move gently through neutron stars, pulsars, millisecond clocks, and magnetars, following the strange afterlife of massive stars without rushing the mystery. If this kind of calm science helps you relax, learn, or fall asleep, please like the video, subscribe to the channel, and share it with someone who enjoys quiet cosmic stories. Thank you for spending your time here. Let us know in the comments what time it is where you're watching or listening from, and where in the world you are. Now, let's begin with the collapse of a star. The iron core of a massive star is not born as an object of collapse. It forms slowly, after millions of years of nuclear burning have already shaped the star into layers, each one built from the ashes of the one before it. Hydrogen has given way to helium, helium to carbon and oxygen, and later burning stages have assembled heavier elements under rising temperature and pressure. Near the end, the star begins to resemble a furnace with shells nested inside shells, while the central region becomes increasingly crowded with nuclei that no longer offer the same escape. The crucial point arrives with iron, not because iron is rare or unstable, but because it is unusually final. Fusion has worked for so long because lighter nuclei can merge into heavier ones and release energy. That released energy supplies pressure, and pressure holds the star against its own gravity. Iron changes the balance. Fusing iron does not pay the star back with useful energy. It costs energy instead. Once the core is dominated by iron group nuclei, the center of the star has reached a kind of thermonuclear dead end. The surrounding layers may still be active, still burning in shells, still feeding ash inward, but the core itself has lost the main process that kept earlier stages alive. It does not explode immediately. For a short time, it is supported by a different kind of resistance, a quantum pressure arising from electrons forced into a dense arrangement. This is electron degeneracy pressure, a resistance that does not depend on heat in the ordinary way. It comes from the rule that electrons cannot all occupy the same quantum state. Packed tightly enough, they push back, even as the temperature becomes extreme. For a white dwarf, this kind of support can hold an entire star remnant in balance. In the core of a massive star, it is only a temporary pause. Matter continues to fall inward from the burning shells above. The iron core grows heavier, gravity tightens its grip. The pressure beneath the surrounding star climbs toward a limit where electron degeneracy can no longer carry the burden. This limit is often described through the Chandrasekhar mass, the maximum mass that electron degeneracy pressure can support under these conditions. It is not a hard everyday boundary like the edge of a solid object. It is a threshold in the physics of dense matter, where the available quantum resistance is no longer enough to stop collapse. As the core approaches that threshold, two processes make the situation worse. Energetic photons begin breaking apart heavy nuclei, undoing some of the nuclear assembly that took the star its lifetime to build. This process, called photodisintegration, consumes energy, and that loss removes pressure from the core at the moment pressure is most needed. At the same time, electrons are forced into protons inside nuclei and in the surrounding dense matter, forming neutrons and releasing neutrinos. This process is electron capture. It removes electrons, which weakens the very degeneracy pressure that was supporting the core. Gravity does not need to become stronger. The supports beneath it are simply being taken away. The collapse that follows is not a slow settling. It is a catastrophic inward fall, a change so abrupt that the scale of the core becomes difficult to hold in ordinary terms. A region once comparable to a planet in size shrinks toward the scale of a city. The infalling matter accelerates under its own weight, and the interior is driven into densities close to those found inside atomic nuclei. The empty space that normally separates nuclei and electrons is no longer allowed to remain empty in the same way. Protons and electrons are pressed together. Neutrons become the dominant form of matter. Neutrinos, produced in enormous numbers, begin their escape, though even they are briefly slowed by the density around them. In this instant, the star's center is no longer behaving like a gas, or a plasma, or any familiar material. It is becoming nuclear matter on a stellar scale. Yet collapse also contains the seed of its own resistance. As the density rises toward nuclear density, the newly formed neutrons cannot all be forced into identical quantum states. They develop their own degeneracy pressure, far stronger under these conditions than the electron support that failed before. Nuclear forces also become important at very short distances, adding further resistance once matter has been crushed into extraordinary closeness. The inward plunge does not continue smoothly into nothing. It halts, violently and suddenly, when the inner core becomes too stiff to compress much further. The matter falling inward reaches this stiffening core and rebounds. A shock wave begins to move outward through the star. The story is often simplified as a bounce that blows the outer layers away, but the real event is more delicate and more difficult. The shock wave loses energy as it breaks apart in falling nuclei and struggles through dense material. Neutrinos, carrying away much of the gravitational energy released by collapse, appear to help revive the shock and drive it outward. Even now, the exact details of how every core collapse supernova succeeds remain an active field of study, because the problem involves gravity, nuclear physics, fluid motion, magnetic fields, and neutrino behavior all at once. What is clear is that the outer star cannot remain as it was. The collapse of the core has removed the central support. The layers above fall inward and then are driven outward in a supernova, an explosion that sends newly made elements into space and leaves the compact core exposed. What remains at the center depends on mass. If the collapsed core is not too heavy, neutron degeneracy pressure and nuclear forces can hold it in a new balance. The result is a neutron star, a remnant that carries more mass than the Sun in a volume only tens of kilometers across. If the core is too massive, even neutron pressure fails, and the collapse continues toward a black hole. The boundary between those outcomes is one of the important uncertainties in stellar death, because it depends on the equation of state, the relation between pressure and density inside matter, more compressed than any laboratory can reproduce in bulk. In a neutron star, the former stellar core has not simply become smaller, it has crossed into a different regime of matter. Before collapse, atoms had space, shells, and structure. After collapse, ordinary atomic architecture has been largely erased. The electrons that once helped define atoms have mostly been absorbed into protons. The nuclei that once mark the difference between elements have been crushed into a sea where neutrons dominate. The object left behind is not a glowing star in the usual sense, powered by ongoing fusion. It is a hot, dense remnant, born from the failure of fusion and the success of gravity. Its first moments are turbulent. It radiates immense energy in neutrinos. It may rotate rapidly because the collapsing core preserves angular momentum as its size contracts. It may carry a magnetic field intensified by compression and motion. But before it is a pulsar, before it is a magnetar, before it announces itself through pulses or flares, it is first the answer to a narrower question: What happens when a massive stellar core runs out of energy sources that can push outward strongly enough to balance its own weight? That answer is collapse, followed by a resistance so extreme that matter stops looking familiar. The birth of the neutron star therefore begins not with spectacle, but with a failed bargain. For most of the star's life, gravity squeezes and fusion answers. The core contracts, heats, and finds another fuel. The sequence continues through stages that grow shorter and more intense, until the final ash is iron and the old answer no longer works. From that point, every change accelerates. Pressure weakens, electrons disappear into protons, neutrinos flood outward. The center falls inward so quickly that the surrounding star cannot adjust gently. In less than a breath by human standards, the core leaves behind the physics of ordinary stellar interiors and enters the domain of compact objects. The supernova may become the visible event, bright enough to mark a galaxy, but the hidden transformation at the center is the deeper turning point. A massive star has lost the long contest between weight and heat, and in losing it, has created one of the densest stable objects the universe allows. The newborn remnant is small enough that its size almost hides the violence that made it. A neutron star is not spread across the old outline of the star that collapsed, and it does not fill the space once occupied by the iron core. It is compressed into a sphere only about the width of a large city, yet it may contain more mass than the sun. That contrast is the first doorway into its strangeness. In ordinary life, size and weight tend to move together. A mountain feels heavy because it is large. A planet feels immense because it is wide. A neutron star breaks that habit completely. Its diameter may be measured across tens of kilometers, but its mass belongs to the scale of stars. The result is not merely an object with high density. It is an object in which the usual architecture of matter has been remade, so that the emptiness inside atoms no longer defines most of the volume. Before the collapse, the core of the star was dense by any earthly standard, but it was still made of nuclei, electrons, radiation, and plasma arranged under stellar pressure. After collapse, the scale changes so severely that comparison becomes unstable. The mass of a star has been folded into a region that could fit inside a metropolitan area. If such an object replaced a city on Earth, it would not sit there as a strange compact globe. Its gravity would dominate the planet. Its surface would be only a short distance away by map scale, but physically it would belong to another regime of nature. The city-size description is useful only because it gives the mind a boundary. It should not make the object feel familiar. The density comes from removing the spaciousness that normally makes matter possible in its everyday form. An atom is mostly not matter in the solid sense. Its nucleus is tiny compared with the region occupied by its electrons. The mass is concentrated in that nucleus, while the surrounding electron cloud gives atoms their size, their chemistry, and their ability to form structures. In ordinary material, even iron, even rock, even the deepest metal in a planet, most of the volume is still governed by this atomic spacing. Compression can bring atoms closer, strip electrons away, and create exotic states. But it does not usually erase the distinction between nucleus and electron cloud. A neutron star comes from an event strong enough to do almost that. Electrons and protons have been forced together into neutrons. The boundaries between nuclei have largely lost their old meaning. What remains is matter, packed near nuclear density, extended over a stellar mass. The phrase nuclear density matters because the nucleus of an atom is already where most ordinary mass resides. A neutron star is what happens when matter is not merely made of many nuclei, but brought into a state where the distances between nuclear particles become the main scale of the whole object. This is why small amounts of neutron star material are often described as impossibly heavy. The comparison's imperfect, because material removed from such a star would not remain stable in any ordinary way. Still, as an image of density, it points in the right direction. A spoonful of matter at neutron star density would carry the mass of a mountain, not because the spoonful has become magically heavy, but because the mass that normally occupies a far larger volume has been compressed until the usual empty spacing has almost vanished. The object itself does not rely on chemical bonds, crystal lattices, or molecular strength to hold shape. Those are fragile arrangements compared with the pressure inside a neutron star. Its structure is governed by gravity pulling inward and by quantum and nuclear effects resisting further collapse. This makes the remnant a kind of natural experiment, one that no laboratory can reproduce at full scale. Nuclear physicists can study dense matter in fragments and collisions. Astronomers can measure masses, radii, spin, and radiation. Between those two views lies one of the most important questions about neutron stars. How does matter behave when it is squeezed beyond the density of an atomic nucleus and kept there by gravity? The answer determines how wide a neutron star can be, how heavy it can become before collapsing into a black hole, and what layers might exist beneath its surface. Even the radius is more than a measurement. It is a clue to the stiffness of matter under impossible pressure. If dense nuclear matter is relatively stiff, it resists compression strongly, allowing a star of a given mass to be slightly larger. If it is softer, the same mass can be squeezed into a smaller radius. A difference of only a few kilometers becomes meaningful, because the entire star is already so compact. Within that small range may be information about neutrons, protons, and perhaps more exotic particles under conditions unreachable by any other means. The compactness also changes the way light and space behave around the remnant. The star is not a black hole, because its surface remains outside the point of no return. Light can still leave it, but the gravity is strong enough to bend light severely, so that more of the surface may be visible to a distant observer than would be possible on a normal star. Radiation climbing away loses energy, stretched toward longer wavelengths by the gravitational field. Time itself runs more slowly near the surface compared with faraway space. These are not decorative effects added to the story. They are part of the same compactness that makes the star dense. Mass has been placed into so small a volume that relativity becomes necessary, even before the object becomes a black hole. The neutron star therefore stands in a narrow territory between familiar stars and gravitational collapse without surface. It is not held up by heat from fusion. It is not diffuse enough to be treated like a normal gas. It is not compact enough to hide behind an event horizon. It remains visible, measurable, and yet physically extreme. That is why it can serve as a bridge between fields that rarely meet so directly. Stellar evolution explains how it is made. Nuclear physics tries to describe what it contains. General relativity shapes the gravity around it. Observational astronomy catches the pulses, bursts, cooling light, and orbital effects that reveal its properties. A single city-sized remnant forces all of these languages into the same object. The apparent simplicity of its outline is therefore misleading. From a distance, a neutron star may be no more than a point of radiation, a signal arriving from a supernova remnant or a binary system. In physical terms, it is layered, stressed, hot, magnetic, and relativistic. It may have a thin atmosphere above a solid crust, a deeper crust where neutron-rich nuclei arrange themselves under pressure, and an interior where neutrons may flow with almost no friction. Some models suggest that deeper still, the matter may include hyperons, meson condensates, or deconfined quarks, though none of these possibilities is settled. The small radius does not mean the physics is simple. It means the physics is concentrated. Every kilometre inward may cross a boundary where matter changes its form, not gently, but under pressure rising toward values that make ordinary material categories fail. The city scale also creates a quiet paradox in how neutron stars are imagined. They are often introduced through comparisons that make them sound like condensed versions of familiar objects: a star squeezed into Manhattan, a mountain in a spoon, a solar mass inside a city. These comparisons are helpful, but they can make the remnant feel like ordinary matter made tighter. In reality, the collapse has not simply packed normal atoms closer together, it has changed what those atoms are allowed to be. The old identity of matter has been partly overwritten. There are no mountains in the familiar sense, no glowing surface like a sunlit planet, no stable ground of rock or metal as human experience understands it. There is a surface, but it is a surface of nuclear and gravitational extremity. There is a radius, but that radius is set by the deepest properties of dense matter. There is mass, but mass arranged so compactly that the difference between a neutron star and a black hole may depend on a narrow margin of internal pressure. That margin is what gives the remnant its importance. A neutron star is not only the leftover core of a dead massive star, it is a test of how far matter can be compressed and still remain matter with a surface. It shows that the universe permits an object heavier than the sun to occupy a region that could be crossed in less than an hour on an ordinary road, while also making that region unreachable in any practical sense. The scale is intimate and inaccessible at the same time. Its width can be named easily. Its density cannot be felt, approached, or reproduced. What makes the neutron star so difficult to understand is not that it is large, but that it is far too much in far too little space. The collapse has taken the mass of a star and pressed it into a boundary small enough to imagine, yet the physics inside that boundary remains larger than ordinary intuition can hold. Surface gravity is the first property that makes a neutron star feel less like a small star than a boundary where ordinary motion stops making sense. The remnant may have the width of a city, but its mass is not city scale. It carries stellar mass inside a radius so short that gravity has almost no distance over which to weaken before reaching the surface. On Earth, gravity is gentle enough that falling objects gather speed gradually. Mountains can stand, oceans can settle, and matter can keep the familiar shapes produced by chemistry and temperature. On a neutron star, the same idea of a surface exists only in the most limited way. It is a place where matter ends and space begins, but it is not a place where anything ordinary could rest. The pull downward is roughly hundreds of billions of times stronger than the pull at Earth's surface, depending on the star's mass and radius. This is not only a larger number attached to a familiar experience, it is a different regime of force, one in which the distinction between falling, striking, and being destroyed becomes extremely narrow. A pebble released above such a surface would not drift downward with an arc that could be watched. It would be seized. In a fraction of a moment, it would accelerate to a substantial fraction of the speed of light, because the gravitational well is so deep and the surface lies so close to the mass causing it. By the time the pebble arrived, it would no longer be a pebble in any ordinary sense. It would be compressed, heated, stretched by tidal forces, stripped of structure, and converted into an impact event releasing more energy than its small size suggests. The violence would not come from chemical fuel inside the pebble. It would come from gravitational energy, the energy gained by falling into one of the steepest wells in the visible universe. The same principle applies to anything made of ordinary matter, before it could touch the surface. Different parts of the object would feel measurably different pulls. The side closer to the neutron star would be pulled more strongly than the side farther away. On Earth, this difference exists, but it is small for objects of human scale. Near a neutron star, it becomes severe. This stretching is tidal force, the same basic effect that raises tides on Earth and can tear apart moons or stars near compact objects. Near the neutron star's surface, the effect is no longer gentle or planetary. It can pull matter into thin streams, separating structure from structure until the concept of a solid body has no useful meaning. Even if an object somehow survived the tidal gradient, the pressure at contact would finish what the fall began. The surface gravity would flatten ordinary matter into a layer far thinner than anything built by material strength could resist. Strength itself becomes irrelevant. Chemical bonds, metallic lattices, crystal structures, and molecular frameworks are all too weak compared with the gravitational command being imposed. On a planet, mountains can rise because rock has strength, and gravity is weak enough for that strength to matter. On a neutron star, a mountain is not allowed much height. The crust may support tiny irregularities, but the pull downward forces the surface towards smoothness with ruthless efficiency. What would be a microscopic bump by earthly standards can already represent an enormous stress under neutron star gravity. The surface is therefore among the smoothest known natural surfaces, not because it is calm, but because gravity suppresses relief. Any elevation must fight a downward force so strong that even nuclear-scale material strength is heavily constrained. This gives the neutron star a strange combination of hardness and fragility. Its crust is likely an extraordinary solid, made of nuclei and electrons arranged under pressures that no ordinary material could survive. Yet the gravity pressing on it is so intense that its freedom to form landscape is almost absent. It can crack, strain, shift, and transmit forces, but it cannot grow mountains in the familiar sense. The star is solid enough to have a crust and still too gravitationally severe to resemble a world. The surface also changes the meaning of escape. On Earth, escape velocity is high, but reachable by rockets. Around the Sun, it is higher, but still part of the same broad framework of orbital mechanics. For a neutron star, escape velocity can be a large fraction of the speed of light. Anything leaving the surface must climb out of a gravitational field that has taken most of the object's size and placed it close to most of the object's mass. Light can escape, which is why the neutron star is not a black hole. But light does not leave unchanged. Its wavelength is stretched by gravity, and its path is bent. Photons emitted from the far side can curve around enough that a distant observer may see more than half of the surface at once. The result is an object whose appearance must be interpreted through relativity. The surface is not merely bright or dim, it is optically reshaped by the gravity around it. Pulses from hot spots, cooling radiation from the young crust, and flashes from accreting matter all carry this imprint. The gravity alters the timing, the energy, and the apparent area of emission. In this way, the surface becomes both hidden and revealing. It cannot be approached, but its gravity writes itself into the light that escapes. That light helps astronomers estimate mass and radius, because the depth of the gravitational well affects what can be observed. The difficulty is that many effects overlap: temperature, atmosphere, magnetic fields, rotation, and viewing angle all influence the signal. A neutron star surface is therefore not a simple glowing sphere that can be measured like a distant planet. It is a compact relativistic environment, and each observation must be untangled from the physics that distorts it. The atmosphere, if present, may be extremely thin in mass, yet still important for the radiation that escapes. Under such gravity, even a small amount of gas would settle into a layer of very small height. Elements separate quickly by weight. Light elements, if available, can float above heavier ones, while heavier nuclei sink. The surface composition may depend on the star's history, whether it is young and cooling after a supernova, whether it has accreted matter from a companion, whether magnetic fields have shaped its outer layers, and whether bursts or flares have altered the crust. Each of these conditions changes how heat leaves the star and how radiation is filtered before travelling outward. A surface that seems simple in outline may therefore carry a complicated memory of collapse, cooling, rotation, and environment. Gravity holds all of it close. Nothing disperses easily. Fallen matter does not pile up gently. It is compressed into the existing layers, heated, transformed, and made part of the star's outer record. In binary systems, where a neutron star draws gas from a companion, this becomes especially important. Material spiraling inward forms an accretion flow, heats intensely, and can strike the surface near magnetic poles or across wider regions. The release of gravitational energy can make such systems shine strongly in X-rays. If enough hydrogen or helium accumulates on the surface, nuclear burning can ignite in sudden flashes, producing bursts that briefly reveal conditions in the outer layers. Even there, the central fact remains the same. Gravity is the engine that turns falling matter into radiation. The neutron star does not need to fuse steadily like an ordinary star. Its compactness alone can power dramatic emission when matter is supplied from outside. Yet the same surface that releases this energy also sets a limit. There is no gentle ground beneath the infall, no ocean or rock plain waiting to receive it. There is a compressed crust and a gravitational field so strong that the arriving material is forced into a new state almost immediately. This is why the surface gravity of a neutron star is more than a detail of its size. It governs the shape, the light, the impacts, the atmosphere, and the way the object interacts with its surroundings. It determines how high a surface feature can rise, how fast matter falls, how strongly radiation is shifted, and how thin the outer layers become. It also sharpens the distinction between a neutron star and a black hole. A black hole has no material surface outside the event horizon. A neutron star does. Matter can strike it, heat it, bury itself in it, and reveal it through flashes. But the surface is so extreme that it feels like a last visible boundary before matter would be lost to a still deeper form of collapse. The importance of that boundary lies in its contradiction. It is real enough to emit light, support a crust, and register impacts. It is hostile enough that ordinary material identity cannot survive contact. Gravity there does not merely pull downward, it edits matter into forms allowed by pressure, density, and quantum rules. The star's surface is therefore not a destination but a transformation zone, the place where the universe permits a compact object to remain visible, while almost everything familiar about weight, strength, and falling has already been stripped away. Beneath the severe surface of a neutron star, the word interior begins to lose its ordinary comfort. On Earth, moving downward means passing through rock, mantle, liquid metal, and pressure that grows in a way geology can describe. Inside a neutron star, the inward journey would cross layers where matter is sorted not by minerals or chemistry, but by how much compression it can endure before its identity changes. The outermost material may be a thin atmosphere and then a crust, but even the crust is not familiar ground. It is likely made from atomic nuclei packed into a crystalline lattice, surrounded by a sea of electrons, with gravity pressing every layer so tightly that the spacing between particles is set by forces far beyond solid matter, as normally known. Near the surface, some nuclei may still resemble heavy elements such as iron, because iron group nuclei are among the most tightly bound products left from stellar burning. Deeper down, the pressure grows until nuclei are pushed into increasingly neutron-rich forms. Electrons are forced into protons. Neutrons accumulate inside nuclei in numbers that would make such atoms unstable anywhere else. The crust is therefore not a shell of ordinary metal. It is a pressure-arranged landscape of nuclear matter, where the boundary between one nucleus and the surrounding sea becomes less clear with depth. At a certain point, called the neutron drip region, nuclei can no longer hold all of their neutrons. Extra neutrons begin to leak out and move through the lattice. This is a quiet phrase for an extraordinary transition. Matter has reached a density where the particles that usually remain locked inside atomic nuclei can begin existing between them, forming a fluid that threads through the solid structure of the crust. The star becomes stranger by becoming less separable. There is still a lattice. There are still nuclei, but there is also a sea of free neutrons. And those neutrons may behave as a superfluid, a state in which matter can flow without ordinary viscosity. Superfluidity is not simple slipperiness. It is a quantum condition that appears when many particles move together as one collective state. In a neutron star, this means that part of the interior may rotate in a way that is not perfectly tied to the crust above it. That distinction matters because neutron stars are observed not only as dense objects, but as rotating objects. Some pulsars show sudden jumps in rotation rate, called glitches, and one leading explanation involves interactions between the solid crust and the superfluid neutrons beneath it. The crust slowly loses rotational energy as the star spins down, while the superfluid can hold on to angular momentum in pinned vortices, tiny quantum whirlpools that thread through the interior. When the coupling changes suddenly, angular momentum can be transferred back to the crust, and the observed pulse rate shifts. A tiny irregularity in timing may therefore reveal a hidden arrangement of matter far below the surface. The interior does not announce itself directly. It leaves clues through rotation. Below the inner crust, the lattice is expected to give way to a core dominated by fluid nuclear matter. Here the pressure is so high that even the terms neutron and proton become less settled than they sound. The outer core may contain mostly neutrons, with a smaller population of protons, electrons, and perhaps muons, which are heavier relatives of electrons. The neutrons may remain superfluid, while protons may become superconducting, allowing electric current to move without ordinary resistance. Superconductivity inside such an object is not a laboratory curiosity. It could shape how magnetic fields are stored, threaded, and evolved over time. In a neutron star, magnetism is not merely attached to the surface. It may be rooted in the behavior of charged particles deep inside, locked into dense matter whose quantum state affects the star's long-term evolution. Still, even this picture may be only the outer layer of the unknown. Farther inward, toward the central core, the pressure may exceed the point at which ordinary nuclear matter can remain ordinary. Some models allow new particles to appear, such as hyperons, which contain strange quarks. Others suggest that mesons could form condensates, collective states in which certain particles occupy the same lowest energy condition. Still others propose that neutrons and protons may dissolve into deconfined quark matter, where the quarks normally trapped inside them move through a larger volume. These ideas are not decorative speculation. They arise because matter under such pressure may lower its energy by changing form, and the star's structure depends on which form nature permits. The difficulty is that several possibilities can be made mathematically plausible. While observations have not yet forced a single answer, the hidden core may be nuclear, hybrid, or more exotic than the outer layers imply. The problem is sharpened by the maximum mass of neutron stars. Observations of very massive neutron stars show that the interior cannot be too soft. If matter yielded too easily to compression, these stars would collapse into black holes before reaching the measured masses. At the same time, radius measurements and gravitational wave signals from merging neutron stars suggest that matter cannot be arbitrarily stiff either. The equation of state, The rule connecting pressure and density in the interior must thread a narrow path. It has to hold up heavy stars, allow realistic radii, and match the behavior seen when two neutron stars distort each other just before merging. Every new measurement narrows the space of possible interiors, but the answer remains incomplete. A neutron star is small enough to be described with a single radius, yet complex enough that the radius becomes a coded message from matter that cannot be sampled. The crust also may contain a peculiar intermediate region sometimes called nuclear pasta, where nuclei are squeezed into shapes that are neither isolated spheres nor uniform fluid. Under immense compression, matter may arrange itself into rods, sheets, tubes, and other forms because competing nuclear and electric forces find temporary compromise. The names used for these shapes sound almost playful, but the physics is serious. Such layers could affect how heat travels, how the crust breaks, how neutrinos escape, and how magnetic stresses move through the star. They may also influence the star's ability to support tiny deformations, which in turn could matter for gravitational waves. The interior is therefore not just dense. It is structured by a sequence of compromises, each one set by pressure, quantum rules, and nuclear forces. One layer gives neutrons freedom. Another allows superfluid rotation. Another may reshape nuclei into extended patterns. Deeper still, matter may abandon nuclei altogether. The remnant seems simple only because no telescope can resolve its surface as a landscape. In physical terms, it may be one of the most layered objects known. Heat provides another clue to this buried structure. Young neutron stars are born extremely hot, then cool by emitting neutrinos from their interiors and photons from their surfaces. How quickly they cool depends on what particles exist inside and what reactions are allowed. Certain exotic forms of matter could open faster cooling channels, letting energy escape more efficiently through neutrinos. Superfluidity can suppress some reactions and enhance others at different stages. The observed temperature of a neutron star, especially when compared with its estimated age, therefore becomes another indirect probe of the interior. Cooling is not merely fading. It is a record of which particles are present and how they behave when compressed into a stellar core. This is part of what makes neutron stars so valuable. They're too far away and too extreme to touch, but they perform experiments continuously, and the results arrive as pulses, spectra, bursts, spin changes, masses, radii, and gravitational waves. Each signal is incomplete by itself. Together, they press against the same hidden question. What is matter allowed to become after atoms are erased, after nuclei are strained, after neutrons dominate, and after pressure climbs beyond the scale where ordinary nuclear intuition is secure? The answer may not be a single substance. It may be a layered sequence, with each depth holding a different compromise between collapse and resistance. The crust, then, is not merely the outside of the neutron star. It is the first page of a deeper record. Its tiny height variations, fractures, pinned vortices, magnetic stresses, and possible nuclear pasta all point inward. Beneath it, the core carries the greater mystery, not because nothing is known, but because what is known is enough to show how much depends on what cannot yet be seen. A neutron star is often described as a ball of neutrons, and at the simplest level that is useful, but the true object is more subtle, a compressed archive of nuclear physics, rotating under its own gravity, with a solid crust above fluids that may be superfluid, superconducting, and perhaps something stranger still. The surface marks the visible boundary. The interior decides what kind of object that boundary is able to contain. The rotation of a neutron star begins before the neutron star exists. The massive star that produces it has always turned, perhaps slowly at the surface and differently in the hidden layers beneath. Because stars are not rigid bodies, gas circulates, magnetic fields thread through moving plasma. Inner regions can exchange angular momentum with outer shells over long periods, and stellar winds can carry some of it away. By the time the iron core is ready to collapse, its spin is the remainder of a long history, not a simple inheritance from the visible star. Yet even a modest amount of rotation becomes transformed when the core contracts. This is the same principle that makes a skater spin faster when the arms are drawn inward. But inside a dying star, the change is not graceful or controlled. The core falls from a planetary scale toward the scale of a city, and angular momentum has far less room to spread itself out. If the collapsing matter does not shed enough spin, its rotation rate must rise sharply. The newborn neutron star can therefore emerge turning many times each second, and in some cases far faster, carrying into its first moments the rotational memory of a star that no longer exists. The important quantity is angular momentum, a measure of rotation that depends on mass, speed, and how far that mass lies from the rotation axis. When the core was large, much of its mass was distributed farther from the center. As collapse pulls that matter inward, the same rotational budget is packed into a smaller radius. The speed must increase because the distance is decreased. This does not require a new engine to spin the neutron star up. Gravity supplies the collapse, and geometry does the rest. What had been a slow turn in a broad stellar core can become rapid rotation in a compact remnant. The change is so extreme because radius matters strongly. Reducing the size by a large factor magnifies the spin by an even larger factor if angular momentum is mostly conserved. In reality, the collapse is complicated. Some angular momentum may be transported outward. Magnetic fields may break the core or redistribute spin. Turbulence, convection, and the supernova explosion itself can leave the remnant with asymmetries. Still, the basic direction remains clear. Compression favors acceleration. A neutron star is born not only dense, but wound up. This rotation is not a surface detail. It shapes the object from the beginning. A rapidly spinning neutron star is slightly flattened, with the equator pushed outward compared with the poles. The gravity is so strong that the deformation remains limited unless the spin approaches the breakup limit. That limit is the point at which material at the equator would no longer be held securely by gravity against centrifugal effects. Neutron stars can rotate astonishingly fast without flying apart because their gravity is so intense and their radii are so small. Even then, nature imposes limits. If a star spins too quickly, it cannot maintain a stable shape. Matter, radiation, magnetic torques, and gravitational waves can all become pathways for losing rotational energy. The fastest observed pulsars sit below the theoretical breakup speed, and that gap matters. It suggests that some combination of formation history, accretion physics, internal structure, and energy loss prevents neutron stars from spinning arbitrarily close to the edge. Rotation, therefore, becomes another probe of the interior. The maximum possible spin depends on mass, radius, and the stiffness of dense matter. A star that is larger for the same mass reaches its limit differently than one that is more compact. The way a neutron star turns can quietly constrain what it is made of. At birth, the spin may also be uneven. The crust, mantle, and core are not necessarily locked together at once. A newly formed neutron star is hot, fluid, convective, and threaded by magnetic fields. Its inner regions may rotate at slightly different rates, and that differential rotation can store energy. Over time, viscosity, magnetic coupling, and neutrino emission help the object settle. As it cools and a crust forms, the star becomes more organized, but not perfectly simple. Superfluid components may rotate through quantized vortices, while the crust rotates as a solid shell. The visible pulse, when the star becomes a pulsar, tracks the rotation of the magnetic beam and crustal surface, but hidden layers may carry angular momentum in more subtle ways. This is why a sudden pulsar glitch can be meaningful. A small jump in spin rate can suggest that the star is not rotating as one perfectly rigid body. Somewhere inside, angular momentum has been held back and then released. The clock is precise enough that a disturbance far below the surface becomes observable across interstellar space. Rapid rotation also changes the environment outside the neutron star. A magnetic field attached to a spinning conductor does not simply sit still. It is dragged into motion, twisting the surrounding plasma and generating electric fields that can pull charged particles from the surface or accelerate particles already present nearby. The rotating magnetosphere becomes a structured machine, with open and closed field lines, regions where particles stream outward, and zones where radiation can be produced. This is the route from rotation to pulsar behavior, although the beam itself belongs to later sections of the story. The point here is that spin supplies energy. A young pulsar shines not because fusion has resumed, but because rotational energy is being tapped and converted into particle acceleration, radiation, and motion in the surrounding nebula. The neutron star is gradually spending its spin. Each pulse, each wind of particles, each interaction with the magnetic field draws from the rotational reservoir. The loss is tiny from one turn to the next, but across thousands of years it matters. The star slows, and the changing pulse period becomes a measure of how fast that energy is being drained. A newly formed neutron star may be embedded in the expanding remains of the supernova that created it. Its rotation can help shape that remnant from within. The Crab pulsar offers a well-known example of a compact rotating object injecting energy into a surrounding nebula. The pulsar wind fills the interior with high-energy particles and magnetic fields, producing radiation across the spectrum. In such systems, the neutron star is not just a leftover ember at the center of an explosion. It is an active engine, powered by spin, able to stir the debris of the star that made it. The same collapse that created the remnant also gave it a rotating reservoir of energy that can remain visible long after the supernova light has faded. This is one of the quiet inversions in the life of a massive star. The original star spent its life producing energy through nuclear burning. The remnant spends part of its afterlife losing rotational energy through magnetized outflow. The fuel has changed from fusion to motion. Rotation also affects what astronomers can learn from timing. Because a neutron star is so compact, it can rotate with extraordinary regularity. Once the initial turbulence settles, the remnant behaves in some ways like a cosmic flywheel, storing angular momentum in a dense and stable body. Pulsars are not perfectly unchanging, but their regularity can be remarkable. Careful timing reveals gradual slowdowns, tiny irregularities, orbital motion if the pulsar has a companion, and sometimes subtle signals caused by gravitational effects along the path to Earth. The stability comes from the star's compactness and inertia. It has so much mass in such a small volume that small disturbances usually do not change its rotation very much, yet the same precision makes even tiny changes visible. A neutron star's spin is both stable enough to serve as a clock and sensitive enough to reveal hidden physics. That combination is rare. It turns rotation from a simple descriptive property into one of the main languages through which the remnant communicates. The origin of that language remains the collapse itself. When the iron core lost support, it did not merely become denser, it became smaller while retaining part of its rotational identity. The acceleration that followed was not an added flourish, but a consequence of concentrating mass inward. From that moment, the neutron star carried two linked extremes, density and spin. Density made the surface gravity and internal pressure extraordinary. Spin gave the object an energy reservoir that could be spent in radiation, winds, pulses, and long-term slowing. The rotation may begin as an inherited motion, but after collapse it becomes one of the defining features of the remnant. It determines how the magnetic field is presented to space, how the star loses energy, how its crust and superfluid interior exchange angular momentum, and how observers recognize it from far away. A neutron star without rotation would still be dense, strange, and important. A rotating neutron star becomes something more communicative. It turns its compactness into timing. It turns its magnetic structure into rhythm. The core that collapsed in silence can become a repeating signal, not because it chose to shine, but because conservation laws carried the memory of motion into a body small enough to make that memory rapid. Magnetic fields in a neutron star are not added after collapse, as though the remnant first becomes dense and only later becomes magnetic. They are carried inward from the dying star, compressed with the matter, stirred by rotation, and reorganized under conditions where electrical conductivity is immense. A massive star already has magnetized plasma moving through its interior. Its field may be modest by neutron star standards, but the collapse changes what modest means. When the core shrinks from a broad stellar volume into a city-sized object, magnetic field lines are crowded into a much smaller area. This alone can intensify the field dramatically, because the same magnetic flux is forced through less space. Then rotation enters the problem. The newborn remnant spins rapidly, and any difference in rotation between layers can wind magnetic fields around the star, stretching and amplifying them. Convective motion in the hot young interior may add further complexity, acting for a short time like a dynamo, a system in which moving, conducting fluid strengthens and reshapes magnetism. The result is not a simple bar magnet placed inside a sphere. It is a compact, rotating, highly conducting object whose magnetic structure is tied to matter under extreme pressure. The field may emerge through the surface in tilted patterns, distorted loops, and regions of intense concentration. It can reach strengths millions of times beyond anything produced steadily on Earth, and in some cases far beyond that. The numbers are useful only up to a point. Earth's field is gentle enough that a compass needle can follow it. The Sun's field is strong enough to organize sunspots, flares, and loops of plasma. A neutron star's field is strong enough to change the behavior of the space around it. It pulls charged particles into motion, shapes radiation, and helps turn rotational energy into signals that cross the galaxy. The magnetism is invisible, but it gives the remnant a structure larger than its surface. Around the star lies a magnetosphere, a region dominated by the magnetic field and filled with charged particles, electric currents, and radiation. Because the star rotates, the magnetosphere cannot remain still. Field lines anchored to the crust sweep through space. Some lines close back onto the star, forming loops, while others open outward and allow particles to escape. The real geometry may be more complicated, but the basic consequence is clear. The neutron star is not isolated at its surface. Its rotation and magnetism extend its influence far beyond the physical radius. This outer magnetic environment becomes the stage on which pulsars will later appear. Before the beam is described, the field itself has to be understood as an energy converter. A magnetic field alone does not radiate like a lamp. Rotation provides the stored energy, and magnetism provides a way to extract it. As the star spins, it induces electric fields strong enough to pull charged particles from the surface, or accelerate particles already present above it. Electrons and positrons can be driven along magnetic field lines to enormous energies. A positron is the antimatter counterpart of an electron, with the same mass and opposite charge. In the intense electric fields near a neutron star, particle pairs can be produced in cascades, multiplying the plasma that fills the magnetosphere. These particles follow curved magnetic paths, and when charged particles are accelerated, they radiate. The emitted radiation can range from radio waves to gamma rays, depending on where and how the acceleration occurs. This is one reason neutron stars are observed in many forms. A compact object with no fusion engine can still produce high-energy radiation, because it is spending spin through magnetic machinery. The surface field also sets the scale of how tightly particles are guided. In an ordinary magnetic field, charged particles spiral along field lines with motions that can be redirected by collisions or turbulence. Near a neutron star, the field can be so strong that charged particles are confined to extremely narrow motion across the field. Their freedom is mainly along the magnetic direction. The magnetosphere becomes ordered not because it is quiet, but because the magnetic field dominates the particle dynamics. The stronger the field, the less the surrounding plasma can ignore it. This gives the star's radiation a directional quality. Energy is not released equally in all directions. It is organized by the magnetic poles, by regions where field lines open, and by gaps where acceleration can proceed. When the magnetic axis does not line up with the rotation axis, this organization becomes especially important. The star turns, the magnetic pattern turns with it, and any radiation tied to that pattern sweeps through space. The field also exerts a braking effect. A rotating magnetized neutron star launches electromagnetic waves and particle winds that carry away energy and angular momentum. The star gradually spins down. Its period lengthens. Its rotational reservoir drains. This spin down is not a sign of mechanical friction in the usual sense, because there is no solid surface rubbing against space. It is lost through fields and particles. The magnetosphere acts like a coupling between the star and its environment, allowing the rotation of the compact remnant to be converted into escaping energy. Over thousands or millions of years, this braking reshapes the life of a pulsar. A young neutron star may rotate rapidly and produce strong emission. As it ages, the slower spin and changing magnetosphere can make it harder to sustain the particle acceleration needed for bright pulses. Some neutron stars become quiet, not because their density has changed, but because their rotational energy is no longer being spent in the same visible way. Yet the magnetic field itself may not remain fixed. It can evolve through the crust, decay over time, or be distorted by internal motions. In ordinary stars, magnetic fields are carried by plasma that circulates and changes continuously. In neutron stars, the crust is solid and extremely conductive, so magnetic evolution can be slow and constrained. Currents may persist for very long periods, but the field can still shift, especially if it is strong enough to stress the crust, or if the star accretes matter from a companion. Accreted material can bury magnetic fields beneath fresh layers, alter the surface geometry, and change how the star presents itself. In young neutron stars, strong internal fields may slowly push outward or rearrange. In magnetars, this stress becomes central to the star's behavior. For ordinary pulsars, it still matters because the external field controls how efficiently the star loses spin and how radiation is shaped. Magnetism is therefore not a static label. It is part of the remnant's history, linking birth, cooling, rotation, and environment. The field strength inferred for many pulsars is already beyond familiar comparison, often around hundreds of millions of Tesla at the surface for typical young radio pulsars. Some are weaker, especially recycled millisecond pulsars whose fields have been reduced or buried during accretion. Some are stronger. The measurement is usually indirect. Astronomers estimate magnetic fields by observing how fast a pulsar spins and how quickly that spin changes. A strong magnetic field should break the star more efficiently, so the combination of rotation period and slowdown becomes a clue. This is not a perfect measurement of the true surface geometry, but it is powerful enough to organize neutron stars into families. Young pulsars tend to have stronger fields and long-term spin down. Recycled millisecond pulsars rotate very fast but often carry weaker external fields. Magnetars occupy the upper extreme, where magnetic energy itself becomes a dominant reservoir. The same kind of object, a neutron star, can therefore appear very different depending on how rotation and magnetism are arranged. The magnetic field also affects how radiation leaves the surface. In strong fields, atoms and plasma do not behave exactly as they would in low-field environments. Heat may travel more easily along field lines than across them, producing hot regions near magnetic poles. The atmosphere, if present, becomes directional, meaning radiation can depend on its path through the field. Near the strongest fields, even empty space is not entirely passive. Quantum electrodynamics predicts that the vacuum itself can become birefringent, acting somewhat like a crystal that affects different polarizations differently. This does not turn space into matter, but it shows that neutron star magnetism reaches a domain where quantum theory and astrophysics meet. The magnetic field is no longer only a large-scale guide for particles. It becomes part of the microscopic behavior of light and charge. This is why the awakening of magnetic fields after collapse is a turning point in the story. Density creates the remnant, and rotation gives it a reservoir of motion, but magnetism gives that reservoir a voice. Without a strong magnetic field, a spinning neutron star would be far harder to notice unless it accreted matter or cooled brightly. With magnetism, the star can organize particles into beams, carve structure into its surroundings, lose rotational energy in measurable ways, and leave timing signatures that can be recognized from Earth. The field is the bridge between the hidden compact object and the visible signal. It reaches outward from a surface that cannot be visited, threading nearby space with invisible architecture, making the neutron star more than a dense core left behind by a supernova. It becomes a rotating electromagnetic engine. The next form of that engine is the pulsar, where the tilted field and the turning star combine to make collapse appear as rhythm. The pulse of a neutron star is not a flash from the whole surface turning on and off. It is a matter of geometry. A rotating neutron star may send radiation outward in preferred directions, shaped by its magnetic field, and when one of those beams sweeps across Earth, a telescope receives a brief rise in signal before the beam moves away again. The star has not stopped shining between pulses. The beam has simply turned out of view. This is why the usual comparison to a lighthouse remains useful, even though the object is far stranger than any lamp on a coast. The rotation axis and the magnetic axis are often misaligned. The star turns around one axis, while charged particles and radiation are organized around another. The result is a sweeping pattern, repeated with every rotation, so that a compact remnant only tens of kilometers wide can announce itself across thousands of light years as a rhythm. The rhythm may arrive in radio waves, visible light, X-rays, gamma rays, or several forms at once, depending on the pulsar and the region where its radiation is produced. What makes the pulse recognizable is not only brightness, it is repetition. The signal returns with the same period again and again, often with astonishing regularity, until the distant object begins to resemble a clock made from collapse. The physical origin of the beam begins above the magnetic poles and along open magnetic field lines. Near the surface, The magnetic field is strong enough to force charged particles into narrow paths. The rotation of the star creates electric fields that lift particles from the surface and accelerate them outward. Some particles emit radiation as they curve along magnetic lines. Others trigger cascades, producing more electrons and positrons, which add to the flowing plasma. The details of exactly where the strongest radio emission forms are still debated, but the broad picture is that the magnetosphere is not quiet. It is a moving, charged environment, driven by rotation, threaded by magnetic fields, and capable of turning a fraction of the star's rotational energy into observable radiation. Because the emission is directional, most neutron stars that behave this way are not visible as pulsars from Earth. Their beams miss this planet. They may still be rotating, magnetized remnants, but their geometry hides them. A pulsar, in the observational sense, is therefore not a separate species of object so much as a neutron star whose beam crosses the right line of sight. The same star seen from another part of the galaxy might not pulse at all. This makes every known pulsar partly a discovery of alignment. The universe contains the engine, but detection depends on whether the sweep happens to touch the observer. The pulse profile, the shape of the signal during each rotation, can be more complicated than a single bright spike. Some pulsars produce two main peaks, suggesting that both magnetic poles may be visible, or that the emission geometry has multiple components. Others show narrow pulses, broad pulses, drifting subpulses, or changes in intensity from one rotation to the next. A pulse is therefore not merely a tick. It is a fingerprint of the magnetosphere. Its shape depends on the star's rotation period, magnetic field geometry, emission altitude, particle flow, and the angle from which it is observed. If gravity bends light near the surface, it can also change what parts of the emitting region are visible. If the magnetosphere is filled with plasma, that plasma can alter how radio waves escape. If the magnetic poles are not simple dipoles, meaning not arranged like the two ends of a clean bar magnet, the beam can be uneven or displaced. This is one reason pulsars remain rich objects even after their basic explanation is known. The repeating signal answers the first question, but each pulse carries further structure. It reveals that a neutron star is not only rotating, it is rotating through an electromagnetic environment with its own weather, its own currents, and its own instabilities. The timing of the pulses is the deeper gift. Once a pulsar is identified, astronomers can measure its period with extraordinary precision. A young pulsar may rotate many times each second. An older one may take longer. A recycled millisecond pulsar may turn hundreds of times each second. Whatever the period, the regular arrival of pulses allows tiny changes to be tracked over years. Most isolated pulsars gradually slow down because they are losing rotational energy through radiation and particle winds. This slowing is small, but measurable, and it gives a window into the star's magnetic braking. The period and its rate of change can be used to estimate an apparent age, a magnetic field strength, and the rate at which rotational energy is being lost. These estimates are simplified. Yet they give astronomers a way to compare pulsars across the galaxy. A pulse train becomes a biography written in timing. It records how fast the neutron star turns now, how quickly that turning is fading, and how much energy remains available to power the magnetosphere. In young systems, that energy can be visible around the pulsar as well as in the pulses themselves. A pulsar wind can stream outward, carrying charged particles and magnetic fields into the expanding debris of the supernova. The surrounding nebula may glow because the pulsar continues to feed it from the inside. In this way, the beam seen from Earth is only one part of a larger structure. The same rotating magnetic engine that produces pulses can also inflate a bubble of high-energy particles. stir old stellar debris, and keep a supernova remnant bright long after the original explosion has faded. The pulsar is small, but its influence is not restricted to its surface. The timing signal is narrow. The energy flow can fill a nebula. This difference between compact source and extended consequence is one of the reasons pulsars are so useful. They can be studied as clocks, as particle accelerators, as laboratories of plasma physics, and as markers of stellar death. The pulse also travels through space before reaching Earth, and that journey leaves marks. Radio waves moving through the thin ionized gas between stars are delayed in a way that depends on frequency. Lower frequency waves arrive slightly later than higher frequency waves because they interact more strongly with free electrons in the interstellar medium. By measuring this dispersion, astronomers can estimate how many electrons lie between Earth and the pulsar, and from that infer something about distance and the structure of the galaxy. The pulsar, then, is not only a source, it is a probe. Its signal carries information about the space it crosses. Some pulses are scattered, broadened, or dimmed by turbulence in interstellar plasma. Some are affected by motion in binary systems. Some pass close enough to massive objects that relativistic effects appear in their timing. Every delay and distortion has to be accounted for, but once understood, these effects become measurements rather than nuisances. A pulse that begins as a rotating beam becomes, after careful timing, a thread of information stretching across the galaxy. The regularity can be so strong that pulsars reveal planets, companion stars, and subtle gravitational effects through small shifts in pulse arrival times. The first planets found outside the solar system were discovered around a pulsar, detected not by seeing the planets directly, but by watching how their gravity made the pulsar wobble. In binary systems, pulse timing can show orbital decay, relativistic time delays, and the gradual loss of energy through gravitational waves. Some pulsars therefore test gravity itself. Their beams are not merely signals from exotic objects. They are measuring rods and clocks placed in extreme environments, where the predictions of relativity can be followed over long intervals. This is especially powerful because the neutron star is so compact. A small orbit around another dense object can produce strong gravitational effects, while the pulses provide the timing precision needed to measure them. The lighthouse image is accurate enough to explain detection, but too simple to contain the scientific use of the beam. A lighthouse helps ships know where they are. A pulsar helps astronomers measure what gravity, plasma, motion, and dense matter are doing in places that cannot be reached. Still, the visible elegance of a pulsar should not hide the cost of its order. Each pulse is powered by energy leaving the star's rotation. The clock is slowing. The beam exists because the remnant is losing what collapse gave it. Over time, many pulsars move toward quieter states. Their periods lengthening and their emission weakening as the magnetospheric engine becomes less efficient. Some may cross a boundary where the conditions needed for sustained radio emission fail, leaving a rotating neutron star that no longer announces itself in regular flashes. Others may be revived later by accretion in binary systems, spun up into millisecond pulsars with different fields and histories. For the ordinary young pulsar, however, the pulse is both signal and decline. The star speaks by spending its motion. What arrives at Earth as a precise flash is the controlled leakage of rotational energy from an object born in collapse, organized by magnetism and made visible by chance alignment. The beam sweeps past, the signal rises and falls, and in that narrow rhythm the hidden remnant becomes measurable. The first pulsars entered astronomy not as understood remnants, but as a timing problem. In the late 1960s, radio astronomy was becoming sensitive enough to notice patterns that earlier instruments would have missed. and one of those patterns appeared in the long paper records examined by Jocelyn Bell Burnell at Cambridge. The instrument had been built to study radio sources through the way their signals flickered as they passed through the solar wind. But within the data was a small, repeating trace that did not fit the expected behaviour of ordinary radio noise. It was narrow. It returned. It was too regular to dismiss easily, and yet it didn't resemble the broad, variable radio emission already known from many astronomical sources. The first task was not to explain it, but decide whether it was real. Radio telescopes are surrounded by sources of confusion. Human transmitters leak into observations. Electrical equipment produces interference. The ionosphere can disturb incoming waves. Instruments can generate patterns of their own. A signal that repeats with strange precision must therefore be treated with caution before it is allowed to become a discovery. Bell Burnell and her colleagues checked the timing, the position, the behaviour across the sky, and the possibility that the source came from Earth. The signal kept pointing back to space. That changed the problem. It was no longer a nuisance in the equipment. It was an object, or at least a process, somewhere beyond Earth, sending radio pulses with a regularity that seemed almost mechanical. At first, the regularity made the discovery feel more puzzling rather than less. Natural astronomical objects were known to vary. Stars pulsated, radio galaxies flickered, solar activity could burst and fade. But a pulse arriving again and again with such a short, steady interval suggested something compact, something able to change on timescales far faster than a normal star. The period itself carried a physical constraint. No object can vary coherently faster than light can cross it, because different parts of the object need time to communicate changes. A signal repeating in seconds, or fractions of a second, points toward a source much smaller than the Sun. It does not by itself prove the source is a neutron star, but it rules out many larger possibilities. The pulse forced astronomers to think in terms of compactness before the nature of the object was settled. The early nickname involving little green men was partly a joke and partly an honest admission of surprise, a signal that regular naturally invites thoughts of artificial origin until ordinary causes are tested. Yet the case for intelligence weakened as soon as more such sources were found. A single strange signal might be a technological question. Several sources scattered across the sky, each with its own period, made a natural population much more likely. The repetition was not the signature of a message, it was the signature of a class. Once that shift occurred, the mystery narrowed into physics. What kind of natural object could be small enough, stable enough, energetic enough, and common enough to produce these radio pulses? White dwarfs were considered, because they are compact stellar remnants and can rotate. But many pulsar periods were too short for ordinary white dwarfs to explain comfortably. A white dwarf spinning that quickly would be close to breaking apart, and the energy requirements were difficult. Neutron stars, proposed decades earlier as possible remnants of supernovae, fit the scale far better. They could be small enough to rotate rapidly without flying apart. They could hold immense magnetic fields. They could store rotational energy in a compact body. The strange signal began to point backward toward a prediction that had been waiting for evidence. The discovery did not create the idea of neutron stars. It gave the idea a voice. Before pulsars, neutron stars were plausible but difficult to confirm. The supernova theory allowed for collapsed cores, and nuclear physics suggested that matter could be supported by neutron degeneracy pressure. But a cold, quiet neutron star would be extremely hard to detect. Pulses changed that. They offered a repeating signal with timing that could be measured and compared to the expectations for a rotating compact object. The model that soon became dominant was elegant because it connected several properties at once. A neutron star is small enough to spin rapidly, it can possess a strong magnetic field. If the magnetic axis is tilted relative to the rotation axis, radiation tied to the magnetic poles will sweep across space. When the beam crosses Earth, a pulse appears. The period of the pulse is the rotation period of the star. A mysterious radio rhythm became the turn of a collapsed core. This interpretation also explained why the pulses were stable but not perfectly eternal. A rotating magnetized neutron star should lose energy, causing its rotation to slow gradually. Observations found that many pulsars did exactly that. Their periods lengthened by tiny amounts over time. The slowdown was too small to notice casually, but radio timing could measure it. The clock was not artificial and not perfectly fixed. It was a natural flywheel spending rotational energy through magnetic braking and particle emission. This was a crucial confirmation, because it gave the pulsar a physical life history. A new pulsar could be fast and energetic. An older one could slow and fade. The pulse period and its change could be used to estimate age and energy loss. The object was no longer only a flashing point. It was an evolving remnant. The connection to supernova debris strengthened the case further. The Crab Nebula, a glowing remnant from a supernova observed in the historical sky, contains a pulsar at its center. Its pulses arrive about 30 times each second, and its energy output helps power the surrounding nebula. The Vela pulsar lies in another supernova remnant, and also shows the behavior expected of a young neutron star losing rotational energy. These associations mattered because they tied pulsars directly to stellar death. The theory of core collapse said that neutron stars should be left behind in some supernovae. The observations placed rapidly rotating compact sources inside the expanding remains of such explosions. The pieces began to hold together massive star death, compact remnant, rapid rotation, magnetic field, and pulsed radiation. What had begun as a strange mark on radio records became a new way of identifying the afterlife of massive stars. The discovery also changed the emotional scale of astronomy in a quieter way. A signal that seemed at first almost too orderly for nature turned out to be produced by one of nature's most extreme forms of disorder, a collapsed core, a supernova remnant, a magnetic field strong enough to organize charged particles into beams. The order was real, but it did not come from calm conditions. It came from compactness and conservation. It came from the fact that a neutron star can rotate with remarkable steadiness because it is dense, small, and massive. The pulse was a clean arrival from an object that was anything but gentle in origin. That contrast remains part of the power of pulsars. Their signals can be precise enough to time like clocks, while the bodies producing them were made in explosions that tore stars apart. Precision and catastrophe are not opposites here. One leads to the other. As more pulsars were found, their diversity began to widen the original model rather than erase it. Some pulsed slowly, others quickly. Some emitted mostly in radio, while others were strong in X-rays or gamma rays. Some showed glitches, sudden small changes in rotation that hinted at superfluid interiors and crustal stresses. Some were isolated, and some belonged to binary systems where companions affected their timing. The basic rotating neutron star picture remained, but the population became richer. Pulsars were no longer only proof that neutron stars existed. They became tools for exploring how neutron stars age, how magnetic fields evolve, how dense matter behaves, and how gravity operates in tight binary orbits. The first strange signal had opened a field. Each later discovery made the class less mysterious in one sense, and more valuable in another. The earliest question had been whether the pulses were real. The deeper question became what such precise signals could reveal. That progression is the important movement in the discovery of pulsars. A narrow radio trace had to pass through suspicion, verification, surprise, interpretation. and finally integration into the larger story of stellar evolution. The signal did not arrive with its explanation attached. It had to be separated from interference, distinguished from artificial possibility, compared against compact object models, and placed inside the remains of dead stars. By the end of that process, the pulse was no longer an anomaly floating outside known physics. It was evidence that known physics, pushed into extreme conditions, could make something unexpected and orderly. The sky had not produced a message in the ordinary sense. It had produced a rotating remnant whose beam happened to cross Earth, turning the final collapse of a massive star into a sequence of measured arrivals. A pulsar becomes useful as a clock because it is both small enough to spin quickly and massive enough to resist ordinary disturbance. The beam may be narrow, and the mechanism that produces it may be complex, but once the beam crosses Earth, the arrivals can be timed with a precision that turns a distant neutron star into a marker of cosmic order. This is not because a pulsar is perfectly unchanging. It is not. It slows gradually, it may glitch, it may live in a binary system, and its signal may be delayed by plasma between the stars. Yet those complications can be measured, modelled, and sometimes turned into information. The central advantage remains the compact rotating body. A neutron star has enormous inertia in a very small volume, so its rotation is difficult to disturb at random. Each turn brings the magnetic beam back into view, and each return becomes one tick in a long sequence, over days, months, years, and decades. That sequence can be compared against the best clocks on Earth. Any difference between the expected arrival and the actual arrival carries meaning. It may mean the pulsar is slowing. It may mean the pulsar is orbiting an unseen companion. It may mean the signal crossed a region of denser interstellar plasma. It may even mean that space-time itself has been stretched in a small, passing way. The power of pulsar timing lies in this sensitivity. The pulse does not merely repeat, it repeats well enough that deviations become legible. This is why some pulsars have been compared with atomic clocks, not because their interiors are built like laboratory timekeepers, but because their rotational regularity can rival the steadiness needed for precision measurement. Millisecond pulsars are especially valuable. Many of them have been spun up by accretion from a companion star, leaving them rotating hundreds of times each second with relatively weak external magnetic fields. Their weaker braking means they can remain stable over very long intervals. They're old, recycled objects, yet their timing can be cleaner than that of many young pulsars. A young pulsar may be energetic and bright, but it can also be noisy, with stronger spin-down, glitches, and changing emission. A millisecond pulsar often behaves like a refined instrument left behind by a violent history. Its beam arrives so regularly that a network of such pulsars can be used as a galactic scale timing array. The idea is patient and subtle. If many stable pulsars are timed at once, their pulses form a set of clocks scattered through the Milky Way. A disturbance that affects only one pulsar may belong to that pulsar, its local environment, or the line of sight between it and Earth. But a disturbance that appears in many pulsars in a correlated pattern may point to something larger passing through the space between them and Earth. This is the principle behind pulsar timing arrays used to search for very low-frequency gravitational waves. These waves are ripples in space-time, expected from sources such as pairs of supermassive black holes orbiting each other across cosmic time. They stretch and squeeze distances by extremely small amounts, changing the arrival times of pulsar signals by tiny fractions. No single pulse is enough. The evidence builds through long observation, careful correction, and comparison across many pulsars. The clockwork of collapsed stars becomes a detector larger than any instrument built in one place. Pulsars also suggest a way to locate position, because each one has a distinct period, position on the sky, and timing behaviour, a sufficiently detailed map of known pulsars could serve as a coordinate system. This idea appeared in a symbolic form on the records carried by the Voyager spacecraft, where lines radiating from a central point encoded the directions and periods of selected pulsars. The concept was that an intelligent reader, able to recognize the pulsar periods and their arrangement, could infer the location of the Sun. The idea was elegant because it used natural clocks instead of political borders or human landmarks. Pulsars are spread through the galaxy, and their rhythms are not tied to Earth. They offer a kind of astrophysical address system, anchored in compact remnants. The practical reality is more complicated. Pulsars slow down over time. Their beams can precess or shift out of Earth's view. New pulsars have been discovered in large numbers since those early maps were made, making identification less sparse than it once seemed. Interstellar motion changes position slowly across long spans, yet the underlying idea remains strong. A pulsar is not just a source of radiation. It is a timed beacon with a measurable place in the sky and a period that can be predicted across intervals when its evolution is understood. For spacecraft navigation, pulsars can also offer a natural reference. X-ray pulsars are especially interesting because their high-energy signals can be detected by compact instruments and are less affected by some of the plasma delays that complicate radio waves. In principle, a spacecraft far from Earth could compare observed pulse arrival times with predicted arrival times from several pulsars, then determine its own position without relying entirely on signals from home. This is sometimes described as a galactic positioning method, though it is not a simple copy of satellite navigation around Earth. The clocks are distant neutron stars, not machines placed in controlled orbits. The signals are faint, the measurements require careful timing, and the models must account for the motion of Earth, the spacecraft, and the pulsars themselves. Still, the possibility shows how far the meaning of pulsars has expanded. The same object first noticed as a strange radio rhythm can become part of a navigation framework across interplanetary or even interstellar distances. Collapse leaves a beacon, and the beacon can become a coordinate. The precision also depends on removing every known delay from the pulse's journey. Earth is moving around the Sun, so arrival times at a telescope must be translated to what they would have been at the solar system barycenter, the common centre of mass around which the Sun and planets move. The interstellar medium disperses radio pulses, so different frequencies must be compared to estimate and subtract the delay caused by free electrons. The pulsar may have a companion, so orbital motion can shift the timing through changes in distance and relativistic effects. Even Earth's own clocks, telescope positions, and planetary ephemerids must be accurate. Because a timing error on Earth can masquerade as a change in the pulsar, this is why pulsar astronomy is both cosmic and meticulous. The source may be thousands of light years away, but the measurement depends on details at the observatory, within the solar system, along the interstellar path, and in the neutron star itself. The final timing model is a layered correction, and each layer removes one ordinary cause so that deeper signals can stand out. When the model succeeds, the residuals, the remaining differences between expected and observed pulse arrival times, become the place where discovery can hide. A clean residual may confirm that the pulsar is behaving as expected. A patterned residual may reveal a planet, a companion, a change in dispersion, a gravitational effect, or a limitation in the model. In this sense, pulsars are not clocks because they remove complexity. They are clocks because their regularity makes complexity measurable. The history of pulsar timing has already shown this repeatedly. Binary pulsars have provided strong evidence for gravitational wave emission by showing orbital decay consistent with the loss of energy predicted by general relativity. Pulsars with planets have revealed small periodic shifts caused by orbiting bodies. Millisecond pulsar arrays have opened a path toward detecting slow, gravitational waves across galactic-scale baselines. Each case begins with the same act measuring when the pulse arrives. The simplicity of that act hides the depth of what it can test. A pulse is a timestamp from a rotating neutron star, but in reaching Earth it has crossed gravity, plasma, motion, and time itself. The more precisely it is measured, the more of that journey becomes available to science. There is a quiet irony in using pulsars for navigation and timing. They are born from the failure of stellar balance, from cores that collapse because pressure can no longer resist gravity. Their surfaces are hostile, their interiors uncertain, and their magnetic fields can be severe enough to reshape nearby space. Yet from that extremity comes steadiness. A dead massive star leaves behind a remnant whose repeated beam can help define position, test gravity, and search for waves passing through space-time. The pulse is not calm in origin, but calm in arrival. It comes back again and again, carrying a rhythm that outlives the explosion that made it. As a galactic clock, a pulsar shows that the universe can produce precision without design, not by avoiding violence, but by concentrating matter so deeply that rotation becomes a lasting record. The remnant turns, the beam crosses the dark, and from the spacing between arrivals, a map slowly begins to form. An isolated pulsar spends its rotation slowly, one turn at a time, through a loss that is almost invisible in any single pulse. The beam returns, the period remains precise, and for human observers the object may seem fixed, but careful timing shows a steady lengthening. The star is breaking. It has no air to rub against, no surface dragged by ordinary friction, and no engine choosing to slow. The loss comes from the magnetosphere that made the pulsar visible in the first place. A rotating magnetic field drives currents, accelerates particles, launches electromagnetic radiation, and sends a wind outward through surrounding space. Each of those processes carries away energy and angular momentum. The pulsar pays for its signal from the reservoir created during collapse, and that reservoir is finite. The young neutron star begins with rapid rotation because its core shrank so violently. It may shine strongly because spin and magnetism cooperate to produce beams and particle outflows. But the same cooperation also drains it. The pulse is therefore not only a clock tick, it is a small withdrawal from the remnant's motion. Across thousands to millions of years, those withdrawals reshape the star's observable life. The period grows longer, the spin-down rate changes. The magnetic engine becomes less able to maintain the particle cascades needed for bright radio emission. Eventually, an aging pulsar may approach a region sometimes called the death line, a rough boundary where the available voltage in the magnetosphere is no longer sufficient to sustain ordinary pulsar activity. The phrase sounds sharper than the physics really is, because real neutron stars have different field geometries, surface conditions, and histories. Still, the idea captures an important transition. A pulsar can become quiet not because the neutron star vanishes, but because the mechanism that made it pulse has weakened. The compact remnant remains, dense and magnetic, but its beam may fade below detection or stop being produced in the same way. In this sense, many unseen neutron stars may be former pulsars, still turning in the dark with periods too long, fields too changed, or beams too poorly aligned to announce themselves. Spin down also gives astronomers a way to estimate a pulsar's age, but the estimate must be treated carefully. If a pulsar has slowed steadily from a much faster birth period under simple magnetic braking, then its current period and the rate at which that period is increasing can yield a characteristic age. This number can be useful, especially across large populations, but it is not a perfect biography. The pulsar may not have been born spinning much faster than it does now. Its magnetic field may have evolved. Its braking behavior may differ from the simplest model. Glitches and internal coupling can alter the timing. The age of the surrounding supernova remnant, when known, may disagree with the characteristic age. That disagreement is not failure so much as evidence that neutron star aging is more layered than the simplest clock suggests. A pulsar loses spin through external fields, but its interior, crust, magnetic structure, and environment all shape the details of the loss. The slowdown is real. The meaning of that slowdown has to be reconstructed. For isolated pulsars, the story mostly points toward fading. For pulsars in binary systems, the story can turn in the opposite direction. A neutron star may orbit a companion that evolves long after the supernova. If the companion expands or loses material, gas can flow toward the neutron star. The transfer is often controlled by the gravitational boundary around each star, sometimes described through the Roche lobe, the region within which matter remains bound to one member of the pair. When the companion overflows that boundary, matter can stream toward the neutron star and form an accretion disk. The disk is not merely a supply line. It carries angular momentum, gas spirals inward because it loses some energy, but as it approaches the compact remnant, it can deliver rotational momentum to the star. If the disk rotates in the same direction as the neutron star, the transferred material can spin the neutron star up. This is the recycling process. An old cairn, slowed pulsar can be made fast again by feeding from a companion. The phrase recycled pulsar reflects that reversal. The star is not young, but its rotation has been renewed. Accretion onto a neutron star is extremely efficient because the surface gravity is so strong. Matter falling inward releases enormous gravitational energy before it reaches the surface or is channeled by magnetic fields toward the poles. Such systems often appear as X-ray binaries, bright in high-energy radiation from hot accreting gas. During this phase, the neutron star may be difficult to see as a radio pulsar because the surrounding material interferes with the clean magnetospheric emission. Instead, it shines through accretion. Over long periods, the incoming gas can add mass and angular momentum while also altering the external magnetic field. The field may be buried beneath accumulated material or weakened in its observable dipole component. This matters because a lower external field breaks the star less efficiently. When accretion eventually declines or stops, the neutron star can emerge as a rapidly rotating pulsar with a relatively weak magnetic field. These are the millisecond pulsars, old remnants made fast by companionship. Their existence shows that spin period alone is not a simple measure of youth. A very fast pulsar may be ancient, not newborn, because it has been spun up by matter from another star. The transformation depends on balance. If accretion is too weak or too brief, the neutron star may not gain enough angular momentum to become a millisecond pulsar. If accretion is too strong, radiation pressure, magnetic forces, or unstable flow can interrupt the transfer. The star's magnetic field can stop the disk at a magnetospheric radius, where magnetic pressure pushes against the incoming gas. If that boundary lies outside a certain point, the rotating magnetic field may fling material away rather than allow it to settle, a process known as the propeller effect. If the boundary moves inward, matter can reach the surface more easily and spin up the star. Over time, the neutron star may approach an equilibrium period where the torque from accretion balances the tendency of the magnetic field and radiation to remove angular momentum. This equilibrium depends on the accretion rate, field strength, mass, and radius. The final spin of a recycled pulsar is therefore a record of a long negotiation between gravity pulling matter in, magnetism controlling the flow, and angular momentum being transferred through the disk. Binary evolution adds another quiet complication. The companion that feeds the neutron star is changed by the feeding. It may lose its outer layers and become a white dwarf. It may be stripped down to a very low mass remnant. In some systems, radiation from the pulsar after recycling can evaporate the companion further, producing systems where the neutron star appears to be eroding what remains of the star that revived it. Other binaries hold two neutron stars, formed after both massive stars in the original pair have undergone collapse. In those systems, pulsar timing can reveal relativistic effects and orbital decay, but the recycling history may have occurred earlier, when one neutron star accreted matter from the companion before the second supernova. The population of pulsars is therefore also a fossil record of binary lives. Isolated pulsars show the draining of spin after collapse. Recycled pulsars show how a companion can return rotation to an old remnant. Double neutron star systems show that such histories can survive more than one stellar death. The same compact object appears in different roles because its environment writes new chapters onto its original collapse. The contrast between slowdown and recycling is one of the clearest examples of how neutron stars refuse a single life path. A young pulsar spends rotation and fades. An old neutron star in a close binary may gain rotation and reappear. A strong magnetic field can make a young object bright and rapidly breaking, while a weaker external field can allow an old recycled pulsar to keep exquisite time for billions of years. Accretion can bury magnetism, heat the surface, trigger nuclear flashes, and alter the star's angular momentum. The companion can become a white dwarf, a stripped remnant, or another neutron star. What begins as the same basic object, a collapsed core held up by dense matter, becomes a diverse family because spin is not fixed forever. It can be lost to space. It can be given back by a companion. It can be hidden during accretion and revealed again when the system clears. The pulse period observed from Earth is therefore not merely a present condition. It is the visible end of a history involving collapse, magnetic breaking, orbital evolution, mass transfer, and renewed rotation. The aging pulsar and the recycled pulsar are linked by the same conservation laws, but they move through them in opposite directions. One slowly gives angular momentum away, the other receives it from matter falling inward. Between those two paths lies the broader lesson of pulsar evolution. Even a dead stellar core is not finished being shaped by its surroundings. Millisecond pulsars are old objects wearing the speed of youth. They do not usually begin their lives with the rotation that makes them famous. A newborn neutron star can spin rapidly, but the fastest stable pulsars known today are often products of long companionship, shaped by mass transfer rather than by collapse alone. Their periods are measured in milliseconds, which means the whole star turns hundreds of times each second. That statement can sound almost like a technical detail until the size of the object is remembered. This is not a small laboratory rotor, not a moon, not a compact machine built from light materials. It is a stellar mass packed into a sphere roughly the width of a city, with a crust, a superfluid interior, and gravity strong enough to make ordinary surface motion nearly meaningless. When such an object rotates in a few thousandths of a second, the equator moves at a significant fraction of the speed of light. The star remains intact only because gravity is immense, and the matter inside is bound by pressures far beyond ordinary strength. Millisecond rotation therefore marks a boundary zone. It shows how fast a neutron star can be driven before gravity. Dense matter, magnetic fields, and radiation enforce their limits. The route to that speed usually begins in a binary system. An old neutron star, once slowed by magnetic braking, orbits a companion that eventually gives up matter. Gas flows toward the compact object, forms a disk, and spirals inward. As it falls, it carries angular momentum, and some of that angular momentum is transferred to the neutron star. Over long intervals, the remnant is spun up, turn by turn, until it reaches periods that would tear less compact bodies apart. This process is called recycling because it restores rapid rotation to an aging neutron star. But the word is almost too gentle for what is happening. Matter from another star is heated to extreme temperatures. Guided by magnetic fields, compressed by gravity, and used to accelerate a collapsed core, the companion loses mass. The neutron star gains spin. When the accretion phase ends, the system may reveal a millisecond pulsar old, stable, and extraordinarily fast. One nearby example is PSRJ 0437-4715, a millisecond pulsar that rotates in about 5.75 milliseconds. That means it completes more than 170 turns each second, a rate that would be violent for any ordinary object, and yet can be remarkably stable in a neutron star. Its nearness makes it valuable, not because it is visually impressive, but because precision measurements become easier when the signal is strong. Timing, parallax, orbital motion, and the influence of its white dwarf companion can all be studied in detail. It belongs to the pattern expected from recycling a neutron star paired with a white dwarf remnant, evidence that the companion once transferred material and was stripped down during binary evolution. The system is quiet compared with a young supernova remnant, but its quietness is part of its usefulness. A recycled pulsar can keep time so well because it has already passed through the turbulent stages that made it fast. At the faster end of the known population lies the pulsar catalogued as PSRJ 1748-2-446 AD, located in the globular cluster Terzan 5. Its period is about 1.4 milliseconds, corresponding to roughly 716 rotations each second. The number is not simply a record, it is a physical challenge. For a neutron star with a radius of only several kilometers, that rotation implies an equatorial speed around 15% of light speed, depending on the exact radius. The surface is not loose material sliding around a sphere. It is part of an object whose gravity and internal pressure hold it together. But the centrifugal effect at the equator becomes meaningful. The star is still below the expected breakup limit, yet close enough that the observation matters for dense matter physics. If neutron stars could not be stable at that rate, the object would not exist in the form observed. Its rotation therefore places a constraint on the possible mass and radius, and on the equation of state that determines how dense matter resists compression. Fast spin turns the star into a test. It asks how compact and how stiff the remnant must be to survive. The absence of even faster confirmed pulsars is also informative, though less direct. Theoretical limits often allow neutron stars to spin somewhat faster than the fastest observed examples, depending on their mass and interior physics. If the limit is not yet reached, then something in their history may prevent further acceleration. Accretion may stop before the star reaches the true breakup rate. Magnetic torques between the disk and the magnetosphere may set an equilibrium period. Gravitational waves from tiny deformations or internal oscillations may carry away angular momentum at high spin rates. Instabilities in the star's fluid could also drain rotational energy if conditions allow. None of these possibilities alone has settled the question for the whole population. The fastest pulsars do not only show what neutron stars can do, they also point to what may stop them. A limit can be written into nature either by mechanical breakup or by a long balance of torques that prevents the star from reaching that edge. Millisecond pulsars are often less strongly magnetized at the surface than young ordinary pulsars. This weaker external field is part of why they can remain so steady. A strong magnetic field breaks a pulsar more quickly by extracting rotational energy. A weaker field allows the star to keep its rapid spin over enormous spans of time. The field may have been reduced or buried during the accretion phase, when fresh material accumulated over the magnetic poles and altered the external dipole pattern. The star is not unmagnetized. It still needs magnetospheric structure to produce pulses, but its braking is gentler, and that gentleness preserves the rotation. This creates distinctive contrast. Young pulsars can be energetic, irregular, and strongly slowing. Millisecond pulsars can be ancient, fast, and exquisitely stable. Their speed does not mean they are newly born. It often means they have been carefully reworked by a companion. Their clocks are old clocks, wound again by falling matter. That stability makes them central to pulsar timing arrays, where many millisecond pulsars are monitored together for tiny correlated shifts that may reveal very low-frequency gravitational waves. The fastest members are not always the best timers, because signal strength, pulse shape, binary effects, and intrinsic noise all matter. Still, the class as a whole is unusually powerful. Their rapid periods create many pulses to average. Their weak braking reduces long-term drift. Their old age often means fewer violent internal disruptions. A millisecond pulsar can become a quiet reference point in a moving universe. Its signal is not perfectly simple, but it is repeatable enough that tiny errors in prediction become meaningful. In this way, the remnant's extreme rotation becomes a tool beyond the study of the star itself. It helps measure companions, search for gravitational waves, refine planetary ephemerids, and test the stability of clocks on Earth. The interior of a millisecond pulsar must also respond to the speed. Rapid rotation changes the star's shape, making it slightly oblate, wider at the equator than at the poles. This flattening affects the gravitational field and the emission geometry. In close systems, the rotation can interact with accretion flows, magnetic poles, and surface heating. In some transitional millisecond pulsars, systems have been observed switching between accretion-powered X-ray behavior and rotation-powered radio pulsar behavior. These objects reveal the boundary between the recycling phase and the clean pulsar phase. They show that a neutron star can move back and forth between modes, depending on how much matter arrives from the companion and how the magnetosphere responds. The transition is not a simple on and off state. It is a competition between incoming gas and the rotating magnetic field. When accretion dominates, gravitational energy lights the system. When the magnetosphere clears enough space, rotational energy can again drive the pulsar beam. Such systems make the recycling story visible while it's still unfinished. At the highest speeds, every part of the neutron star's history seems to converge. The original collapse supplied compactness. The dense matter equation of state supplied resistance. The companion supplied angular momentum. The magnetic field regulated accretion and later shaped the beam. The interior stored rotation with possible superfluid complexity. The result is an object that turns hundreds of times each second without losing its identity as a star remnant. Nothing about that should be treated as ordinary simply because the pulses arrive regularly. Each millisecond period is the endpoint of a long sequence of constraints. The star must be compact enough not to break apart, old enough to have been recycled, weakly braked enough to keep its spin, and favourably aligned enough to be detected. The surface racing at a fraction of light speed is therefore not a spectacle detached from the rest of the story. It is the visible edge of a deeper balance. Millisecond pulsars show that neutron stars can be driven close to their rotational limits and still remain precise, patient, and measurable. They are remnants of catastrophe turned into clocks, accelerated by companions, held together by gravity, and kept just below the point where speed would begin to undo them. A magnetar begins as the same kind of remnant as any other neutron star, but one part of its inheritance overwhelms the rest. Its magnetic field is not merely strong enough to shape the magnetosphere or produce ordinary pulsar emission. It is strong enough to become the main store of visible activity, strong enough to stress the crust, alter the behavior of atoms near the surface, and make the surrounding vacuum participate in the physics of the object. The star is still compact, dense, and rapidly formed from collapse. It still has a surface only tens of kilometers across, and an interior governed by pressure beyond ordinary nuclear matter. But in a magnetar, rotation is no longer the dominant engine in the usual pulsar sense. Many magnetars rotate more slowly than young radio pulsars, with periods measured in seconds rather than fractions of a second. And yet they can produce bursts of X-rays and gamma rays far more intense than their modest spin would suggest. That difference is the clue. A normal pulsar spends rotational energy. A magnetar spends magnetic energy. The field itself becomes the reservoir, wound through the crust and interior, slowly evolving, pushing, twisting, and sometimes breaking through the limits of the star that holds it. The origin of such fields is still studied, but the most common picture begins in the first moments after core collapse, when the newborn neutron star is extremely hot, fluid, convective, and possibly rotating very rapidly. Under those conditions, a dynamo may operate, turning motion inside the conducting matter into magnetic amplification. If the initial rotation is fast enough and the internal motion strong enough, the magnetic field may grow to values far above those of ordinary neutron stars. Another possibility is that the progenitor star already carried an unusually strong magnetic field, which was then compressed during collapse. These ideas are not mutually exclusive, and real magnetars may not all have identical origins. What matters for the visible object is the outcome magnetic fields reaching around 10 billion to 100 billion Tesla at the surface in many estimates, and perhaps even stronger inside. These values are difficult to compare with familiar magnets because familiar magnets belong to a world where atoms keep their shape. Around a magnetar, the field can become a condition of the environment, not a background influence. It decides how charged particles move, how radiation travels, and how stresses are stored in the crust. In such fields, atoms are no longer shaped mainly by the same balance that governs ordinary chemistry. The magnetic force on electrons can dominate their motion across the field, squeezing atomic orbitals into elongated forms. A hydrogen atom near an extreme magnetic field would not have the rounded probability structure described under normal conditions. It would be stretched along the field direction, narrowed across it, and made into something closer to a thread of charge than an ordinary atom. This does not mean magnetars are surrounded by familiar gases simply warped into strange shapes, because the surface and magnetosphere are far too extreme for easy comparison. But the atomic example shows the scale of the change. Magnetism has become strong enough to interfere with the microscopic architecture of matter. It also affects light. In the strongest fields, the quantum vacuum can behave as if it has optical properties, changing how different polarizations of light move through it. This effect, called vacuum birefringence, is predicted by quantum electrodynamics and becomes relevant in the magnetic surroundings of neutron stars. The field does not create matter out of emptiness in a simple sense, but it makes empty space less passive than ordinary intuition expects. Around a magnetar, even the path of a photon can carry information about the invisible magnetic structure it has crossed. Magnetars were first recognized through their high-energy behavior, rather than through a complete theory of their fields. Some appeared as soft gamma repeaters, sources that released repeated bursts of gamma rays and X-rays. Others were identified as anomalous X-ray pulsars, objects whose X-ray output could not be explained by ordinary spin-down power alone. The word anomalous marked a mismatch. Their rotation did not provide enough energy to account for their radiation, so another reservoir had to be involved. Over time, these classes were understood as related expressions of magnetar activity. The same underlying object could produce persistent X-ray emission, short bursts, longer outbursts, and in rare cases giant flares. The pulse period still matters, because the star rotates and the emission can be modulated by hot regions or magnetospheric structure. But the energy source points inward to magnetic decay and reconfiguration. The field slowly evolves, and as it does, it heats the crust, drives currents in the magnetosphere, and stores stress that can be released suddenly. A magnetar therefore does not need to be spinning hundreds of times each second to be luminous. It shines because its magnetic field is changing. The crust of a magnetar is caught between strength and strain. Neutron star crust is already extraordinary, a dense lattice of nuclei and electrons under immense pressure. In a magnetar, magnetic stresses can be large enough to deform or crack this crust, especially if the internal field shifts over time. The crust is not free to move easily. Gravity presses it flat, dense matter resists deformation, and the magnetic field threads through it like a tension structure. When the field changes, the crust must respond. Sometimes that response may be gradual, producing heating and persistent emission. Sometimes it may be sudden, producing a burst. The physical picture is not exactly the same as an earthquake on Earth, because the materials, forces and scales are entirely different, but the comparison helps in one limited way. Stress accumulates until a rigid layer can no longer maintain its old configuration. Then energy is released. In a magnetar, that energy can be enormous because the magnetic field stores so much of it. A small rearrangement in the crust or magnetosphere can produce a large signal in high-energy light. The magnetosphere of a magnetar is also different from that of an ordinary rotation-powered pulsar. The external field can be twisted, carrying electric currents that heat the surface and scatter X-ray photons to higher energies. Instead of a relatively simple dipole gradually draining rotational energy, the magnetar may have complex magnetic loops and evolving current systems. These structures can trap particles, change the observed pulse profile, and brighten or fade over time. An outburst may begin when the magnetic field rearranges, injecting energy into the magnetosphere and heating part of the surface. The star then slowly relaxes, with emission declining over months or years as heat diffuses and currents decay. This long fading is part of what distinguishes magnetars from simple explosive events. They can flare suddenly, but they can also remain altered afterward, as though the magnetic disturbance has left the outer layers and surrounding fields in a new state that takes time to settle. The field is not only a cause of bursts, it is a changing architecture with memory. Magnetars are rare compared with the full population of neutron stars, at least in the forms that are easy to identify. Only a limited number are known in the Milky Way and nearby galaxies, though many older or quieter magnetars may have faded beyond recognition. Their active lifetimes are thought to be relatively short on astronomical scales because extreme magnetic fields decay and dissipate energy. A magnetar may therefore be a young phase of some neutron stars, brightest while its magnetic reservoir remains intense. As the field weakens or becomes less active, the object may become harder to distinguish from other neutron stars. This possibility blurs the boundaries between categories. Some high magnetic field pulsars show magnetar-like bursts. Some magnetars emit radio pulses for a time. The classes are useful, but nature does not always keep them sealed. Rotation-powered pulsars, accreting neutron stars, and magnetars may represent overlapping outcomes shaped by birth field, spin, age, environment, and magnetic evolution. The name magnetar identifies the dominant behavior, not a completely separate origin. What makes magnetars especially important is that they reveal magnetic energy on a scale almost nowhere else accessible. Stars have magnetic fields. Planets have magnetic fields. Accretion disks and galaxies contain magnetic structure, but a magnetar compresses magnetic intensity into the neighborhood of a neutron star surface, where gravity, dense matter, quantum electrodynamics, and high-energy radiation all meet. It is not simply the strongest magnet in the universe as a phrase of scale. It is a place where magnetism becomes a controlling physical condition, able to influence the crust beneath it, the plasma above it, and the light passing through it. In ordinary pulsars, magnetism gives rotation a voice. In magnetars, magnetism speaks for itself. The star may turn slowly, but the field remains restless. It stores the memory of birth, threads through matter that is already near the edge of collapse, and releases energy when its own structure can no longer remain fixed. The emergence of magnetars therefore widens the story of neutron stars. Collapse can produce dense remnants. Rotation can produce clocks, but magnetism, when amplified to its highest known stellar form, can produce a different kind of object, a neutron star whose most powerful behavior comes from invisible stress, stored in fields strong enough to make matter and light answer to them. Starquakes begin with a difficult fact about magnetars: their crust is strong, but their magnetic field is stronger in the ways that matter most. The crust is not a rocky shell floating above a familiar interior. It is a dense, rigid layer of nuclear material, pressed by gravity into near smoothness and threaded by magnetic stress from below and above. In ordinary experience, a crack is a sign of weakness in a material. In a magnetar, a crack may be the surface expression of a field that has spent years or centuries trying to rearrange itself through matter that resist easy motion. The magnetic field can twist, drift, and shift as currents evolve inside the star. When the field pushes against the crust can flex only so far. It is held down by gravity, locked into dense structure, and coupled to a magnetosphere that may also be twisted. Over time, stress accumulates. The surface does not need to move by a large distance for the energy released to be immense. The reservoir is not the size of the fracture. It is the magnetic energy connected to it. A tiny failure in the crust can open a route for a much larger rearrangement of the magnetic field, and that rearrangement can appear across the galaxy as a burst of high-energy light. The word starquake is useful because it suggests sudden stress release, but it should not make the event feel too much like geology. Earthquakes happen in rock, along faults, driven by plate motion and the slow release of elastic strain. A magnetar quake happens in matter compressed to nuclear densities, under gravity that permits almost no landscape, with magnetic fields strong enough to alter atoms and control charged particles. The analogy is a doorway, not a full explanation. What breaks may be the crust itself, or the magnetosphere may become unstable and force the crust to respond, or both may act together. The details remain under study because the surface cannot be seen directly, and the interior cannot be sampled. What can be measured is the sudden arrival of X-rays and gamma rays, the changing pulse profile, the fading afterglow, and sometimes the way the star's rotation appears to shift after the event. These are the traces left by a hidden mechanical and magnetic adjustment. A magnetar flare can begin with a spike so brief that the main energy releases over almost before ordinary language can follow it. High-energy photons rush outward from the disturbed magnetosphere, and if the flare is large enough, instruments across the solar system may register it. After the initial spike, a softer tail can follow, modulated by the rotation of the star. That modulation matters because it ties the flare to the spinning magnetar itself. The fireball of trapped plasma and radiation may be held temporarily by the magnetic field, rotating with the star as it cools and fades. This picture shows how powerful the field must be. Radiation pressure that would escape freely in many environments can be confined by magnetic loops near the surface, at least for a short time. The flare is not simply light leaving an explosion. It is light, plasma, magnetic structure, and rotation acting together. The strongest known events are called giant flares, and they are rare enough that each one becomes a landmark. One of the most important occurred on December 27th, 2004, from the magnetar known as SGR 1806-20. The source was tens of thousands of light-years away, on the far side of much of the Milky Way from Earth. Yet the burst was strong enough to affect spacecraft detectors and disturb Earth's upper atmosphere. It briefly compressed the magnetosphere, the magnetic bubble surrounding this planet, and produced measurable changes in the ionosphere, the ionized layer high above the surface. That does not mean Earth was in serious danger from that event. Distance softened it into a scientific disturbance rather than a catastrophe. But the fact that a crustal and magnetic disturbance on a neutron star so far away could leave a measurable signature near Earth shows the scale of the release. Most astronomical events that affect the local space environment come from the Sun. A magnetar giant flare can make itself noticed from across a large fraction of the galaxy. The energy in such a flare is not produced by ordinary fire or by fusion suddenly restarting. It comes from magnetic stress. Over time, the magnetar's internal and external fields can store enormous energy in twisted configurations. When those configurations change, part of that energy can be converted into radiation, particle motion, and crustal heating. The total energy released in the earliest moment of a giant flare may rival what the Sun emits over a very long interval. Yet it emerges from a region only a few tens of kilometers across. This contrast is central to magnetars. The source is small, the field is immense, the release is brief. The consequences can travel across interstellar distance. Even smaller bursts follow the same deeper logic. A modest fracture or magnetic reconnection event may produce a short flash. A larger rearrangement may produce an outburst lasting longer, with the surface and magnetosphere remaining bright as they relax. The magnetar behaves less like a steady lamp and more like a stressed system that occasionally finds a new configuration by releasing stored energy. Reconnection is one important idea in this process. In magnetic reconnection, field lines change their arrangement, converting magnetic energy into heat and particle acceleration. The Sun does this during flares, when tangled magnetic fields in the corona reorganize and release energy. On a magnetar, the field strengths are vastly greater and the environment is much more compact. A twist in the magnetosphere can load the field with current. A sudden rearrangement can accelerate particles and produce high-energy emission. If the crust beneath shifts at the same time, the event may connect the solid star to the surrounding plasma in a single release. The distinction between crustquake and magnetospheric reconnection may not always be clean. The crust anchors the field stresses the crust. The magnetosphere responds to both. A flare may therefore be a coupled failure of the outer neutron star and the magnetic structure around it. Giant flares also raise the question of danger. A magnetar close enough to Earth could, in principle, deliver damaging high-energy radiation to the atmosphere. It could disturb chemistry, affect ozone, and expose the biosphere to increased radiation indirectly through atmospheric effects. But known magnetars are not close enough to pose that kind of threat, and the events themselves are rare. Their importance is scientific, not immediate hazard. They show what happens when magnetic energy stored around a compact object is released suddenly. They also help astronomers estimate how many magnetars may exist, how often they flare, and how much energy is hidden in their internal fields. A giant flare can be so bright that, if observed in another galaxy, it might resemble a short gamma-ray burst unless its distance and repeating source are recognized. This possibility matters because some brief high-energy events may come from magnetars outside the Milky Way, rather than from merging compact objects. The same class of star, born in collapse and shaped by magnetism, may therefore leave signals that can be confused with far more distant cataclysms. After a flare, the magnetar is not always exactly as it was before. Its persistent X-ray brightness may change. Its pulse shape may shift, suggesting that hot regions on the surface or currents in the magnetosphere have been rearranged. Its rotation can show timing irregularities, including glitches or changes in spin down rate. These after effects are valuable because they show the flare as a process rather than a single flash. Heat deposited in the crust can leak outward over time. Magnetospheric currents can decay. The field can settle into a less twisted state. By watching the fading emission, astronomers can infer how heat moves through the crust and how the external magnetic structure relaxes. The flare becomes a probe of the star's outer layers. It briefly illuminates the relationship between crust, field, and magnetosphere. The same relationship that is usually hidden behind steady X-ray emission or silence. The violence of the event is real, but the scientific value lies in the cooling, the timing, and the slow return toward quiet. Starquakes and giant flares complete the magnetar's contrast with ordinary pulsars. A pulsar uses rotation to make a stable rhythm, spending its spin through beams and winds. A magnetar can spend magnetic stress in irregular bursts, sometimes producing more energy in one moment than rotation alone could supply. The pulse of a pulsar is orderly because the star turns. The flare of a magnetar is sudden because the field changes. Yet both are forms of the same underlying object, a neutron star, compact enough to make gravity severe, dense enough to make matter unfamiliar, and magnetic enough to connect a hidden crust to distant detectors. In a giant flare, the surface of that object becomes less like a boundary and more like a trigger. A small shift in a crust no wider than a city can release energy through a magnetic structure larger than the star itself, and the signal can cross thousands of light years before brushing the instruments and atmosphere of another world. The crack is local. The consequence is not. The unfinished physics of neutron stars gathers at the places where observation becomes precise and interpretation remains unsettled. After the collapse has been described, after the density has been named, after pulsars and magnetars have been separated into their recognizable behaviors, the central problem is still not closed. A neutron star is visible enough to time, weigh, and sometimes map indirectly. But the most important matter inside it is hidden beneath a surface that no probe can reach. The signals that escape are shaped by gravity, magnetic fields, temperature, rotation, atmosphere, and geometry before they ever cross interstellar space. Each measurement therefore arrives as both evidence and puzzle. A mass is not only a mass, it constrains the pressure deep inside. A radius is not only a size, it hints at how stiff nuclear matter becomes when compressed beyond the density of atomic nuclei. A pulse profile is not only a repeating flash. It carries information about hotspots, magnetic poles, light bending, and the star's orientation. The difficulty is not that neutron stars are silent, it is that they speak through layers of translation, and every translation has to be understood before the hidden core can be read. One of the sharpest unsettled questions is the equation of state, the relationship between pressure and density in matter, squeezed past ordinary nuclear limits, This relation decides how much mass a neutron star can support, how small it can become, and when it must collapse into a black hole. Observations of neutron stars with masses around twice the mass of the Sun show that the interior cannot be too easily compressed. It must be stiff enough to hold up those heavy remnants. Yet measurements from X-ray pulse modeling and gravitational waves from neutron star mergers suggest that the radius is not enormous, which means the matter cannot be stiff without limit. The true equation of state must pass between these constraints. It must allow heavy stars and moderate radii, resist collapse without making the star too large, and match the way merging neutron stars deform each other before contact. If the interior contains only neutrons, protons, electrons, and muons, one set of answers becomes possible. If hyperons appear, or if quarks become deconfined in the deepest core, the pressure may change in ways that soften or restructure the star. The central question is not whether exotic matter sounds interesting. It is whether nature can include it while still producing the massive neutron stars already observed. Gravitational wave astronomy has added a different kind of evidence. When two neutron stars spiral together, they do not behave as perfect points. Each star distorts the other through tidal forces, and the amount of distortion depends on the stiffness of the matter inside. A softer star is more compact and less easily deformed. A stiffer star is larger and more deformable. The final moments before merger therefore carry information about the same dense matter equation that shapes isolated neutron stars. After merger, the outcome also matters. The remnant may briefly become a hypermassive neutron star before collapsing, or it may form a black hole quickly, depending on the masses and the interior pressure. Light from the merger, produced by neutron-rich debris and radioactive decay, reveals that these collisions can forge heavy elements. But beneath that chemical importance lies the deeper physics of support and failure. The merger asks how much mass-dense matter can hold when rotation and heat briefly help it resist gravity. The collapse to a black hole, if it follows, marks the point where even those temporary supports are no longer enough. In that final transition, the neutron star's hidden equation of state becomes a cosmic event. Magnetic geometry is another unsettled layer. The simplest drawings of pulsars show a dipole field, with one magnetic pole in the northern hemisphere and one in the southern hemisphere, tilted relative to the rotation axis. That picture explains the lighthouse effect well enough to begin. It is not always enough to explain real neutron stars. X-ray observations of hotspots on some pulsars suggest magnetic poles that may be offset, distorted, or arranged in ways more complicated than a clean dipole. In at least one carefully studied case, modelling pointed toward hot regions both lying in the same broad hemisphere, a result that does not fit the simplest textbook image. This does not mean the basic pulsar model fails. It means the surface magnetic field may contain stronger local complexity than the large-scale dipole suggests. A neutron star can look simple from far away while carrying tangled multipolar structure near the crust. That complexity matters because hotspots, particle acceleration, pulse shape, and magnetic evolution all depend on the field geometry. Magnetars make that problem still more severe. Their fields may be twisted, buried, fractured, and evolving, with internal components much stronger than the external dipole inferred from spin down. A magnetar that appears to rotate modestly may hide magnetic energy deep inside, stored in toroidal fields wrapped around the star or in tangled structures left from its birth. These hidden fields could explain why a magnetar can produce outbursts long after its rotation has become too slow to power them. But the field cannot be opened and inspected. Its presence is inferred from bursts, pulse profiles, surface heating, polarization, and long-term changes in X-ray brightness. The invisible structure must be reconstructed from the ways it disturbs matter and light. The field evolves slowly until a sudden flare reveals that the quiet surface was holding more tension than it seemed. The timing of pulsars also leaves open questions. Some rotate with extraordinary steadiness, while others glitch, wander, or change emission modes. A glitch may point to superfluid vortices shifting inside the star, but the exact mechanism depends on how the crust couples to the inner fluid, how vortices pin and unpin, and how angular momentum moves through layers that cannot be seen. Some pulsars switch between radio states, changing pulse shape or brightness, in ways that suggest the magnetosphere can reorganize globally. Others stop and start in irregular patterns. These changes show that the pulsar engine is not a fixed lighthouse with simple machinery. It is a plasma system connected to a rotating, magnetized, layered star. Small changes near the surface may alter particle flow across the magnetosphere. Hidden interior changes may appear as timing jumps. The pulse is regular enough to be a clock, but unstable enough to reveal that the clock has weather inside it. Even the surface is still under investigation. A neutron star may have an atmosphere only a small amount of mass, yet that atmosphere can determine how radiation leaves. It may be made mostly of hydrogen if the star has accreted light elements, or of heavier elements if its history is different. Strong magnetic fields change atomic structure and radiation transport. Surface temperature may be uneven, guided by magnetic field lines that carry heat more efficiently in some directions than others. Observations of thermal emission must therefore separate true size from atmospheric filtering, hotspot geometry, and gravitational light bending. The radius inferred from such observations is not read directly from a photograph. It is recovered through models, and the models depend on assumptions that can be tested but not ignored. This is why different methods are valuable. X-ray timing, radio timing, gravitational waves, optical counterparts, and nuclear experiments on Earth all approach the same object from different angles. Agreement among them would be powerful. Disagreement would not be failure, but a sign that some hidden assumption needs to be changed. The unfinished nature of neutron star physics is therefore not a weakness in the story. It is the reason these objects remain central. They sit at a rare intersection where the life cycle of massive stars, the structure of atomic nuclei, the behavior of quantum fluids, the curvature of space-time, and the power of magnetic fields all become inseparable. A neutron star is small enough to turn hundreds of times each second, heavy enough to bend light around itself, dense enough to question the identity of matter, and magnetic enough in some cases to disturb space across interstellar distances. Each signal catches one aspect of the object while leaving the rest partly veiled. The known facts are already extreme collapse creates a compact remnant. Neutron pressure and nuclear forces hold it up. Rotation can make it pulse. Accretion can recycle it. A magnetic stress can make it flare. Beyond those facts lies the harder region where certainty thins. The core may be ordinary nuclear matter pushed to its limit, or it may contain particles and phases not yet confirmed in bulk. The magnetic field may appear simple at large scale while becoming intricate near the surface. The crust may be nearly smooth and still capable of cracking under invisible stress. The pulses may keep time with astonishing precision while carrying small irregularities from deep inside. The final meaning of neutron stars is held in that balance. They are explained well enough to be recognized, measured, and used as tools, but not so completely that their interiors have surrendered. They remain visible boundaries around hidden physics, the last stable form of stellar matter before gravity can become a black hole. The story ends not with a lack of understanding, but with a more exact kind of mystery, one framed by evidence, narrowed by observation, and still waiting at the core. The remnant at the centre of this story is small in outline and immense in meaning. A neutron star begins where a massive star can no longer answer gravity with heat, and from that failure comes a body where matter is pressed into one of its most extreme surviving forms. Its density changes the meaning of size, its gravity changes the meaning of a surface. Its hidden layers carry questions that reach into nuclear physics, quantum fluids, and the edge of collapse. When it rotates, the remnant can become a pulsar, turning the memory of a dead star into pulses measured across the galaxy. When it is fed by a companion, it can be spun up again, becoming an ancient clock with a period measured in milliseconds. When its magnetic field dominates, it can become a magnetar, storing invisible stress until the crust and magnetosphere release energy in sudden high-energy flares. Each form is different, yet each belongs to the same deep family of compact stellar remains. What makes neutron stars enduring is not only that they are extreme, it is that they are still partly readable. Their pulses can be timed, their flares can be measured, their mergers can shake space-time, their light can carry the imprint of gravity, atmosphere, and magnetic fields. Science has given these objects firm edges, and yet those edges surround interiors that remain unresolved. The core may hold matter in forms not yet confirmed anywhere else in nature. The surface may hide magnetic patterns more intricate than simple drawings allow. The crust may be almost perfectly smooth and still capable of sudden strain. In that balance between evidence and concealment, neutron stars remain calm but demanding objects. They're not ordinary stars anymore, and not black holes yet. They are the visible threshold where matter resists gravity one more time.